Alright, I want to take a look at sample problem 5.03, and it's just the derivation for the acceleration of this block right here. What's the acceleration? But the example is one, not really straightforward. It kind of says, well, what happens if we do this? What happens if we do this? And it can be a good learning experience for some, but I'm not a big fan of how they do it. And I got a lot of questions about the homework problems that were like this. I think there was one in the last homework. And I totally get why. So they say, okay, the acceleration is going this way, but this one's going this way. Therefore, on our free body diagram, even though the tension's going up, they want us to flip the tension going down and mg going up. Well, that is like counterintuitive to everything I've taught you. We don't have to make any assumptions like that, and we can get rid of that by using our datum. It's very simple. Datum comes in handy when we have like lots of pulleys. So we could have something like this, where all these pulleys are holding up a block, some mass m, and a force is being applied. Now when we put a tension or a force on this cable in this scenario right here, it's not going to move as far as we pull the cable. So if I pulled this 1 meter, the block is not going to go up 1 meter. It's going to go up in a relationship according to the pulley arrangement, the number of pulleys and the arrangement. And the same for the acceleration and speed. If I pulled this up with some velocity, it's not going to go up with the same velocity. It's going to go up with some relationship. And this is dependent motion. Okay, so we have one object's motion dependent upon the other. They're connected by an inextensible cord. In that case, whatever was pulling and doing the force was our second body we were referring to. But we can use that on this problem. I showed you in the Atwood machine where it's basically just like this, except the pulley's hanging from the ceiling, and you have M1 and some M2, and as long as they're not equal, if you release it from rest, it's going to accelerate. And I showed you that we drew the datum down to 1 as minus S1 and minus S2. So this is what we called our datum. Now let's do that on this one. I'm still going to call the pulley, the center of the pulley, the datum, and I'm going to say, okay, this is going to be the datum that we're going to refer to for the x direction, and this will be the datum that we refer to for the y direction. The reason being, all the pulley is doing is actually changing the direction for us, and this part on the pulley ends up being constant. We can label it some length CD if we want to. But let's see what happens when we do that. So if you remember, for the datum, we basically use the fact that this length that goes over the pulley down to the next mass is a constant value. So it's a constant length. And we can say that the total length of that string is equal to some, we'll measure from the datum to the left, some S1, and then from the datum down to mass 2, and we'll call that some S2. Now, when I add up the string length, I'm going to call this a negative S1 and a negative S2, because the way we do our coordinate systems, this is up. So if I measured down, it would be negative, and we call this to the right. So if I was to measure to the left, it would be negative. We can also add in this little length right here that goes over the top of the pulley. We'll call it some length CD. Now when we take the time derivatives, the length is constant, so that just goes to 0. But the position goes to minus B1 and minus B2. And then this length over the top of the pulley is a constant also, so it just goes down to 0. Alright, what we get is a relationship that says B1 is equal to minus B2, or B2 is equal to minus B1. We can take second derivatives of this and get the acceleration of 1 is equal to the negative acceleration of 2. We're going to use the acceleration of 2 is equal to the negative acceleration of 1 to solve this problem. So there's one equation. Took 2 lines, 1, 2 to get there, I guess 3. And it makes you not have to assume anything. We don't have to assume directions. Just use what I've taught you. Right is to the positive x direction, and up is the positive y direction. Then we don't have to do any weird tricks like saying the tension's actually pointing downward. No, on the free body diagram for this thing, the tension's definitely pointing up. So let's do those. Let's do the free body diagrams. So let's do one on mass 1 first. On mass 1, we have a mass 1 times gravity pointing down, a normal force going up, and then some tension going to the right. In this problem, we're just going back to the basics to show you this thing, the datum, and how it's going to help. So I'm not going to include friction, but there could be a frictional force going to the left if the object's moving to the right. There could be, the mass could be attached to a spring, and we would just put that on our free body diagram and add that in when we do Newton's second law. So on mass 2, we have m2g going down, and then just the tension going up. Now I don't have to do anything. We don't have to flip those. Let's just do Newton's second law. We're not going to get anything from the y direction other than what the normal force is, and it's a flat horizontal surface. There's no friction. We don't need the normal force. So let's just look in the x direction. That's going to give us mass 1 times the acceleration of 1. And I'm keeping subscripts on the acceleration. We have a tension going to the right, and that's it. And that equals mass 1 times the acceleration of 1. I'll call this equation number 1. This will be equation number 3. And let's look at mass 2. We sum the forces in the y direction. We have the mass 2 times the acceleration of 2. Now we have a tension going up, so it's positive, and m2g going down, so it's negative, and that all equals mass 2 times the acceleration of 2. Remember, we do not say t is equal to mg. We do not say that that is equal to 0. That's not the case. It would, if it's not accelerating or moving, that's the case. But we have some sort of acceleration that's going to happen if this was released from rest or initially moving. So don't say that t is equal to mg. What we do get from this is an equation that the tension is equal to m2a2 plus m2g. Now you might want to factor these out, but let's not just yet. Let's use this equation right here. The acceleration 2 is actually in the negative direction. So I get the tension is equal to mass times minus acceleration 1 plus mass 2 times gravity. Now this and this we can set equal to each other. Here's equation 2. Doing so, I get m1a1 is equal to m2, write it like this, m2g, this term, minus m2a1. Now let's gather the acceleration terms on the same side. That'll give me an m1a1 is equal to, m1a1 plus m2a1 is equal to m2 times the acceleration due to gravity. Factoring the acceleration out gives me this, and then let's divide by this combined mass m1 plus m2. It's going to give me the acceleration of block 1 as the small mass, or the hanging mass, times gravity over the combined masses. Ta-da! And if we were interested in the acceleration of 2, instead of using this equation right here, that acceleration of 2 is equal to minus acceleration of 1, we would use acceleration of 1 is equal to minus acceleration of 2, and substitute this up into there. That would be our third equation. And what we would find out is we would just get a minus sign in front of this. So the acceleration of 2 is equal to, I just did it, but it's one of the masses times gravity over the combined mass. And there's a minus sign in front. So check it out. And that makes sense, right? It's going down. Don't quote me on that one, though. Quote me on this one. So there you go. The datum doesn't force us to make any assumptions. It doesn't say, okay, well, we always use this rule, except for this time, do this. The datum allows us to use the same rules. We're going to call up positive, the right positive, and it just happened we needed this one equation. That can be common sense to some people, but honestly, I don't like doing it that way. I think if you can set a standard problem-solving method, it should work for every problem you work on. So even though this is not in our book, the datum is really important for what we call dependent motion. One object moves in direct relationship to the other one, right? They're connected. If one goes over an inch in this case, the other one's going to go down an inch. In a more complicated pulley system like I drew earlier, if one went up an inch, the other might go up a quarter of an inch. If there are maybe 4 pulleys, 1, 2, 3 pulleys, I think. It depends on the configuration too. Alright, so I hope this clears it up. I had quite a few questions about this. I wouldn't assume we're done with hanging masses yet, right? Alright.